In the previous episode, we discussed quantum observables and how they are related to operators. In this episode, we will talk about the conception of measurement in quantum mechanics. Quantum mechanics is known for a number of experiments with a counterintuitive result. We have already spoken about the double-slit experiment, which revealed the wave nature of quantum particles. Now I'm going to talk about the other important experiment, which reveals two more basic quantum properties. This is the experiment conducted by Stern and Gerlach in 1922. They measured the intrinsic magnetic moment of silver atoms. They shoot the atom beam through the inhomogeneous magnetic field, which deflects particles depending on their magnetic moment projection on the z-axis. Higher the projection, the stronger was deflection. It is obvious that if particle has some magnetic moment, its projection on some axis should be distributed randomly and equally, and in experiment we should see continuous picture of their distribution. However, the striking result was that magnetic moment can be only in two states. Let us say up and down for definiteness. In other words, the magnetic moment projection quantizes. It can be only in discrete states, but cannot have every value between them. Another thing is that atom exists not either in up or in down state, but it can be in both up and down states simultaneously. This is the crucial point of quantum mechanics. The value of the particle properties usually is not known before the measurement. It is not as we just do not know this value. It do not actually exist before the measurement. This state is called superposition. So, before measurement, the atom is in the superposition of the states, up and down. During the measurement, the superposition collapses towards some value. Here comes the second key point. Measurement in quantum mechanics is not just querying the system parameters, but necessarily altering them. If before measurement the particle was in the superposition of states, both up and down, after measurement it can be either in up or in down state. Such a situation also called preparation of state, as after experiment you definitely know at what state is your particle. So, firstly, that experiment shows that quantum particle can be in superposition of states simultaneously in several states. Secondly, the measurement in quantum mechanics is a special procedure during which you not only gain the value of some system parameters, but also put the system into this particular state. The another consequence of the measurement is that it can disturb other system parameters. For example, you remember that we have showed that uncertainty in determination of coordinate and momentum obeys the following inequality. In other words, you cannot measure both momentum and coordinate. Is it the only values that cannot be measured simultaneously? The answer is no. Let's repeat the Stern-Gerlach experiment. Let's measure firstly the z projection of the magnetic moment, then separating only up atoms, then measure the x projection separating the right states. For instance, what value of the z projection will give us the next measurement? Classical answer is up. Since we have already separated these states, we know both x and z projection, up and right. However, as you have guessed, the quantum answer is that we will get 50% up and 50% down. The case is similar to the momentum and coordinate variables. You cannot know simultaneously both z and x projection of the magnetic moment. Measuring x projection cancels the knowledge about the z projection, and there are plenty of such examples in quantum mechanics. All I talked about was just experimental results. How do we describe it exactly? What is the mathematical representation of this data? As you already know, every observable of measurable parameter corresponds to some operator in quantum mechanics. The measurement is equivalent to acting by operator on the wave function and choosing one of the possible options of observable, which is the wave function collapse. Operator is an object that acts on the function producing some another function. Though symbolically this procedure looks like multiplying, it obeys other rules. One of the important one is that acting by operating is not permutable. In general case, let's take operator A and operator B. Operator AB is not the same as operator BA. In other words, if you act by operator B on the function f, then act by operator A on the result, the final function would differ from the result of acting by A at first and B then. It is not so surprising as one can think. For example, if A is an operator of putting on the shoe on the right foot and B is an operator of putting on the sock on the same foot, operator AB acting on the foot is normally dressed foot. However, operator BA is a sock put on the shoe. Strange thing, don't you think? In that case, we say that operators A and B commute with each other. The difference AB minus BA is denoted in the following way and called commutator. Let's do some math. As you know, operator of the momentum along x-axis is equal to the derivative with respect to x multiplied by minus IH. The coordinate operator is just multiplying by x. What is the commutator of these operators? Px acting on some function f gives us following. Xp acting on the sum function f gives us this equation. The commutator acting on f is equal to the following expression. In other words, commutator of x and p operators is equal to IH, so these operators do not commute. What about commutators Px, Py? Px, Py acting on some function f gives us the following expression. Py, Px acting on the same function gives us this result. The commutator Py, Px is equal to 0, as you can see. So these operators commute with each other. How are commutators connected with experiments? As you already know, you cannot measure simultaneously both coordinate and momentum of the particle, the observable operator of which do not commute. However, you can measure every projection of the particle momentum which do commute. So, the quantum theory states that two observables can be measured simultaneously if and only if their operators commutate with each other. As another example, you can look backward to the Stern-Gerlach experiment and easily conclude that operators of projection of magnetic moment on the different axes do not commutate with each other. So, summarizing the talk, what we can learn from it. At first, that the particle can be in several states simultaneously, but the measurement breaks the coexistence and choose one of the states randomly, changing the particle state. That is one of the key differences between classical and quantum mechanics. Measurement cannot be made without altering the state. The next is that not every variable can be known simultaneously. Only the observables which operators commute can be measured simultaneously. In the next episode, we will talk about the way we can calculate the wave function and define its evolution in time.